Hi, I'm Chris, and I'm back. In this video I'm finishing up the Verilog code to multiply two 16-bit floating point numbers. If this is the first video from this series which you have seen, you may want to watch the previous videos before watching this one. In the upper right hand corner of your screen is a link to the playlist for this video series. As a refresher, in the last video I wrote the Verilog code for how the multiplication operator handles multiplying by nands, infinities, and zeros. All that's left to do before we have a simple multiplication circuit is to implement the multiplication of normal and subnormal numbers. To do this, I need to finally explain how normal and subnormal numbers are encoded. Before talking about normal and subnormal numbers, I'm going to take a detour into talking about scientific notation. This might seem to be unnecessary, but be patient with me. There are several points about IEEE floating point numbers which I want to make, and I think comparing their behavior to scientific notation will simplify the task. Assume for a moment that we want to calculate the area of a circle. The formula is well known. It's pi times the radius squared. Let's also assume that the radius is 20 centimeters. Since the IEEE 16-bit floating point number format supports about 3 decimal digits of precision, I'm going to use 3 significant digits for the computation of the area, and I'm going to write all of our input numbers in scientific notation. So I'm going to write the radius as 2.00 times 10 to the first power, and for pi I'm going to use the value 3.14 times 10 to the 0 power. Let's start by squaring the radius. Reviewing the steps for multiplying two numbers in scientific notation, we start by multiplying the two mantissas. 2.00 times 2.00 is 4.0000. Look for a moment at how we perform this computation by hand. To determine where the decimal point goes in the final product, we count up the number of digits to the right of the decimal point in both our multiplicand and multiplier. 2.00 has 2 digits to the right of the decimal point, and since this is both the multiplicand and the multiplier, the total number of digits in the product to the right of the decimal point must be 4. Now that we've computed the product of the significand, I'm going to truncate the result to 4.00 since we're only allowing 3 significant digits of precision. The next step is to add the exponents. In this case we're adding 1 plus 1, so the number is 2. I know, you're in awe of my powers of mathematical computation. So the square of 2.00 times 10 to the 1 power is 4.00 times 10 squared. Now let's multiply the radius squared by our approximation of pi. 3.14 times 4.00 is 12.5600. Again, multiplying two numbers which have 2 digits each to the right of the decimal point yields a product which has 4 digits to the right of the decimal point. For now, I'm not going to truncate any digits from this result. Adding the exponents this time, we have 0 plus 2, so the sum is 2. This makes our intermediate result 12.5600 times 10 squared. But this isn't proper scientific notation because we have more than one digit to the left of the decimal point. We have to normalize the mantissa by moving the decimal point one position to the left. Now for the mantissa to have 3 significant digits, we would normally round the mantissa to 1.26. I'm not going to do that. I'm just going to truncate. Then we need to adjust the exponent by the number of places we move the decimal point. Our final result for the area is 1.25 times 10 to the third power centimeters squared. I want to point out several things. In scientific notation, for any non-zero number, there must be only one non-zero digit to the left of the decimal point. This is why when I multiplied by pi, I had to adjust both the mantissa and the exponent. According to the IEEE standard, the significand is treated like the mantissa in scientific notation. We're only allowed to have one non-zero digit to the left of the binary point. The first lesson this leads to is that from time to time we're going to have to renormalize the significand by moving the binary point, and then we'll make a corresponding adjustment to the exponent for the product. Look at the various leading digits I used in the example of calculating the area of a circle. In the various steps, the non-zero leading digits we saw were 1, 2, 3, and 4. Decimal numbers have the digits 1 through 9, which can be used as non-zero leading digits. How many choices of non-zero leading digits do we have in the binary number system? We all know that binary only supports two digits, 0 and 1, so in binary there is only one non-zero digit which we can use as our leading digit, the digit 1. Since we know that the leading digit in our significand is always going to be a 1, there's no need to store the digit. In the IEEE standard, it's implied. For normal numbers, the 10 bits stored in the significand represent only the fractional digits. To create the full significand, we prepend a 1 point in front of the 10 bits stored in the significand. Even though we only store 10 bits, when it's time to actually multiply, the two significands are 11-bit values, and both of these 11-bit values will always have 1 as their most significant digit. Before talking about the exponent, I need to clarify what I mean by the size of a number. For the purpose of the following discussion, I only care about a number's magnitude. What do I mean by this? Minus 30 is less than 0.1, because if you draw the number line, minus 30 is plotted to the left as 0.1. But minus 30 has a bigger magnitude, that is, the absolute value of minus 30 is greater than the absolute value of 0.1. The magnitude is the absolute value of a number. Now let's go back to how the exponent is encoded. Again, let's look at scientific notation. For numbers which are 1 or greater in magnitude, the exponent in scientific notation will be 0 or positive. For numbers which have a magnitude less than 1, the exponent will always be negative. In our previous discussions of the IEEE format, I've always talked about the exponent as an unsigned number. Since the IEEE standard treats the exponent field as an unsigned number, we need some way of making a negative exponent to represent the numbers with a magnitude smaller than 1. The IEEE standard does this by using a bias value. When we extract the exponent field from a floating point number, the actual exponent is computed by subtracting the bias value. For the 16-bit floating point format, the bias value is 15. So the exponent field values of 1 to 30 after subtracting the bias value really represent the exponent values minus 14 to plus 15. Let's go back to the radius value we used when we calculated the area of a circle. The number 20 written in binary with 11 bits of precision is 10100.00000000. For this value, the exponent would be 0, but, like scientific notation, we're only allowed to have one digit to the left of the binary point. So we shift the binary point 4 positions to the left and add 4 to the exponent, so this number is now written as 1.0100000000 times 2 to the 4th power. Let's code this into a 16-bit floating point number. To begin, the number is positive, so the sign bit is 0. Next we take the exponent value of 4 and add the bias value of 15. This is 19. 19 written as a 5-bit unsigned binary number is 10011. We never need to store the leading one digit in the significand field of a normal number, so our significand becomes 0100000000. Concatenating the sign, exponent field plus the bias adjustment, and the fractional bits of the significand, we determine that the number 20 is represented by the floating point value 01001100000000 or 4D00 in hexadecimal. Now let's tackle subnormal numbers. For normal numbers, the smallest exponent field value is 1. When the value stored in the exponent field is 1, the actual exponent being represented is 1 minus the bias value, which is 1 minus 15, which is minus 14. The smallest value which can be stored in the significand of a normal number is binary 1 followed by 10 zeros. What happens if we want to store an even smaller number? We fall into the realm of subnormal numbers. The 1985 version of the IEEE specification called these numbers denormalized, and I think that's actually more descriptive of how they work. For normal floating point numbers, we always have one non-zero digit to the left of the binary point. That is, they're normalized. Subnormal numbers don't have an implied one digit, which gets prepended to the significand. They're denormalized, meaning they have an implied zero instead. The most significant one digit of a subnormal number is explicitly stored in the significand field. The largest magnitude subnormal number only has 10 significant digits. The smallest magnitude subnormal number only has 1 bit of precision. Now let's look at a subnormal number which has bit 9 of the significand set to 1. I'll leave the remaining bits of the significand unspecified because they have no impact on the mechanics of subnormal numbers. This number represents 0.1 ABCDEFGHI times 2 to the minus 14th power, where the digits A, B, C, etc. are arbitrarily set either to 0 or to 1. This number doesn't have any non-zero digits to the left of the binary point. We fix this by moving the binary point one place to the right, and we adjust the exponent by subtracting 1. So this number represents 1.ABCDEFGHI times 2 to the minus 15th power. Next case. Let's make the first two digits of the significand be 0, 1 and leave the remaining 8 bits unspecified. This number represents 0.01 BCDEFGHI times 2 to the minus 14th power. Again, we have to shift the binary point to the right until we have exactly one non-zero digit to the left of the binary point, and we have to subtract the number of places we move the binary point from the exponent, so this number represents 1.BCDEFGHI times 2 to the minus 16th power. Likewise, if the significand field has its first three digits set to 001, the number stored represents 1.CDEFGHI times 2 to the minus 17th power, and so on until we get to the significand 000000001, which represents 1 times 2 to the minus 24th power. So the smallest non-zero numbers we can represent using the 16-bit floating point format are plus or minus 1 times 2 to the minus 24th power. Remember, we support negative numbers too. It's time to go back to the Verilog code. The last case we handled in our multi-branch if statement was the case where we multiplied 0 times a 0, a subnormal number, or a normal number. What's the smallest normal number? It's 1.0000000000 times 2 to the minus 14th power. If we multiply the smallest normal number by itself, we get 1.0000000000 times 2 to the minus 28th power. We've just seen that even for subnormal numbers, the smallest exponent we can represent is minus 24. The exponent value minus 28 is too small to be represented by even a subnormal number. The magnitude of all the subnormal numbers is even smaller than the smallest normal number. So if we're multiplying any two subnormal numbers together, the product is going to have a magnitude which simply rounds down to 0. Consequently, we can add another case in which we know in advance that the product will be 0. The condition on this if statement has been expanded so that not only is the product 0 when one of the operands is 0, but also when both of the operands are subnormal. This is the revised checklist of the cases we've resolved. We're down to just subnormal times normal, normal times subnormal, and normal times normal. You'd like to think that after dealing with the product of two subnormal numbers there weren't any serious complications left, but there are a few. To finish off these last three cases, I'm going to start with normal times normal. It's an easier case to deal with than the other two, and there are lessons we'll learn from this case, which will help us solve the other two cases. Assuming both of the input operands A and B are normal numbers, we need to construct the 11-bit significand from the 10 bits which are actually stored. I first declare two 11-bit vectors and we construct the full significand using the following. Next we need to extract the exponent field. When we do this, we'll subtract the bias at the same time. I'll leave the reasons for doing this as an exercise to the viewer. The exponent field is 5 bits wide. When we perform computations using the two exponents, how many bits will we need? The range of exponents coming into our two operands run from -14 to +15. When we add the two exponents together, how many bits do we need to hold the result? Let's say both of the operands have the most positive exponent. The most positive value for the two exponents is 15. If both exponents have the maximum value of 15, when we add them together we get 30. But remember, we may need to renormalize, so we could see exponents as large as 31. To store 31 requires a minimum of 5 bits, but that's not enough room. Since we're going to handle negative exponents, we need room for a sign bit at the front, so we require at least 6 bits to store the sum of the two exponents. I know where this discussion is going to end, so I'm going to cheat and tell you that I know that even 6 bits isn't going to be enough. We really need a minimum of 7 bits to hold the sum of both exponents. This is the code which declares the locations to hold the exponents of a and b, and the code which initializes their values. Notice that we didn't have to tell Verilog how to build a subtraction circuit. It did that for us automatically. To hold the exponent and significand values for a and b, I've added 6 relatively simple lines of code. Once again, I'm going to cheat. I know that the code for extracting the significand and the exponent is going to get more complicated. So rather than putting the code to extract the significands and the exponents in line in the HP-mul module, I'm going to move it to the HP class module and have the HP class module perform the task of extracting the significand and the exponent at the same time it calculates the type flags. This way I won't have to duplicate the code. This is one of the recurring themes of this series. Using modern hardware design tools is more like writing software than building hardware. Good software engineering practice dictates the avoidance of duplicating code. When new features are to be added, and there will be new features added to this code, or when bugs are found, and I still produce bugs, the code only has to be fixed in one place. We need 2 more temporary variables to hold intermediate results, and then we can finally begin to do some actual multiplication. We need a holder for the sum of the two exponents, and we need a holder for the product of the two significands. The first of these is easy. We just add the declaration of the temporary variable p_exp to the declaration statement for a_exp and b_exp. How much space do we need to store the product of the two significands? The rule is that if you multiply a number which is m bits wide by a number which is n bits wide, you'll need m plus n bits to hold the product. Since we're multiplying two 11-bit significands, we'll need 22 bits to hold the result. Okay, we have a 22-bit significand product, and we have to figure out how to store that as a 10-bit field in the result. The IEEE specification describes several different rounding modes. I'm trying to keep things simple, so I'm not going to bother with rounding at this stage. I'm just going to truncate the result. But before we can do that, we need to find the most significant bit of the product, which is set to 1. In our final result, this 1 bit will become our implied 1, and the 10 bits following it will be stored in the result. Now comes the tricky part. Which bit in raw significand is the most significant bit which is set to 1? I suppose we could make some sort of loop in hardware test the most significant bit, and if the bit is 0, then shift the whole thing left and try again. But that's a brute force approach, and maybe we can do something a little more elegant. What do we know about the significand? First, we always have an implied leading 1, so both a sig and b sig have their most significant bit set. What about the other 10 bits? The two extremes are that the other 10 bits are all 0 or all 1. The smallest product is going to be the square of the smallest possible significand value, and the largest product is going to be the square of the largest possible significand. We also know that our two 11-bit significands have 10 bits to the right of the binary point. The largest significand value is 1, .1111111111. If we multiply this value by itself, we get 11.1111110000000001. The multiplicand had 10 digits to the right of the binary point. So did the multiplier. This means that the product must have 20 bits to the right of the binary point, and it does. Also note something else. In this case, the most significant bit set is bit 21, assuming the least significant bit is numbered as 0. The smallest possible significand value is 1.0000000000. If we multiply this number by itself, the product is 1.00000000000000000000. Here the most significant bit set is bit 20. This means that we never have to look past bit 20 to find the most significant bit of the product, which is set to 1. If bit 21 of the product is 0, then there is only one non-zero digit to the left of the binary point. If bit 21 of the product is 1, then the binary point needs to be moved to the left one place, and the sum of the exponents needs to be increased by 1 to compensate. This is getting really long, so I'm going to skip showing the declarations of the various variables needed to hold the intermediate results. Besides, you can see their declarations in the GitHub repo for this video. We've multiplied the two significand fields earlier where the raw significand value was declared. Here we perform the two steps needed for calculating the product, adding the exponents, and renormalizing the significand and exponent if needed. Now we need to figure out which bits to pack into the final result for the product. If the product is too small to be a subnormal number, we return 0 for the product. If the product is too small to be a normal number, we store it as a subnormal number. Remember that we lose bits of precision when we're using subnormal numbers. Those bits of precision are lost when the code performs a right shift on the significand value. If the number is too big to be a normal number, we return infinity. If the exponent value failed the 3 previous tests, the product is a normal number. Remember to adjust the exponent value by the bias amount to convert the exponent back to an unsigned integer value. Only store the fractional part of the significand. Remember that the most significant bit of the significand is implied. As you can see by the updated checklist, we only have 2 cases left: multiplying a subnormal number times a normal number, and multiplying a normal number by a subnormal number. Figuring out how to deal with subnormal numbers took me some time. My first thought was that when the code extracted the significand field, I should just prepend a 0 bit to form the 11-bit significand, and set the extracted exponent value to -14. This creates a problem. I would no longer be guaranteed that either bit 21 or bit 20 of the significand product was the most significant bit set to 1. It occurred to me that if I normalized the significand for subnormal numbers and adjusted the exponent to match, that the product of a subnormal number would act exactly like the product of a normal number. So I need to shift the significand of the subnormal number left until its most significant 1 bit is in the same position as the implied 1 bit of a normal number's significand. The question then becomes, how do I do this efficiently? I needed something like the built-in CLZ intrinsic supported by the GNU C compiler, which would count the number of leading zeros in the significand. This led to a literature search. If I'm writing software for a processor such as ARM or MIPS, each of those CPUs has an instruction for counting the number of leading zeros, but I'm effectively building a subsystem of a CPU, so I don't have any code I can fall back on. As I said in my introductory video, I'm a Verilog newbie. Maybe Verilog has some fast and efficient way to do this. If so, I don't know enough Verilog to know what that is. If there is some more efficient way to do this, please let me know in the comments below. Using my favorite search engine, I found the same algorithm in multiple places. At the moment, the most convenient location I can think of to direct you to is the book Hacker's Delight. There's an Amazon link in the comment section for this video. This book is full of all kinds of tricky little algorithms, and it's likely I'll be citing it again at some point in this series. The first line of code declares the variables used in the loop and initializes them. The algorithm does a binary search of sorts. The significand may have to be shifted up to 10 bits to the left. The algorithm starts by testing the 8 most significant bits to see if they're all 0. If they are, the significand gets shifted 8 places to the left, and the shift count gets incremented by 8. Otherwise, the significand is left unchanged, and the shift count is left at 0. On the next iteration, the code checks to see if the 4 most significant bits are all 0. If they are, the significand is shifted left 4 bits, and the shift count is incremented by 4. The procedure is repeated 2 more times for the 2 most significant bits, and finally for the most significant bit. When the algorithm is done, the shift count is subtracted from the exponent value minus 14. The normalized significand and exponent are returned to the HP-mul module, and multiplication of subnormal numbers is handled by the same logic circuit that handles the multiplication of normal numbers. Let's revisit my earlier decision to use 7 bits to hold the signed exponent, even though we only needed 6 bits to hold the signed exponent for normal numbers. Consider for a moment that the 2 operands passed into the multiply module are the smallest normal number and the smallest subnormal number. We would need to multiply 1 times 2 to the minus 14th power by 1 times 2 to the minus 24th power. The result is 1 times 2 to the minus 38th power. The most negative number we can store in a 6-bit signed integer is minus 32. I knew I would need 1 extra bit to avoid an overflow when adding these 2 exponents. Of course, the product ends up being set to 0, but the circuit can't know that until after we've added the 2 exponents. If there is an overflow error when adding 2 exponents which have a sum as negative as minus 38, testing the exponent sum could fail, leading to an incorrect value for the product. To avoid overflow when adding negative exponents, I needed to use a 7-bit signed integer field to hold the exponent. Our checklist is now complete. In the next video, I'm going to discuss how the Verilog code gets tested. Questions and comments are welcome in the comments section. If you found this video helpful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.